So hello everyone, we are Group Programmable Storage, and I'm Jojo, and this is Suma, and we are glad to do the final presentation today. And our revisers are Huaicheng, George, and Greg. So to start with, we want to start with the introduction. We are now living in a big data era, and more data are being created each day. People expect that by 2022, around 97 zettabytes of data will be created. It means that we need to process and also store the large data efficiently. So let's first look at the traditional CPU-centric method for processing large data. So they require the data to be copied from the storage device to the memory, and the CPU will be processing on the data, and the results will be written back to the storage after finish. So with too much data to process, there will be too much data transfer. So one natural question to ask is this method still applicable with large data? To find our answer, let's look at the storage development over these years. So from these two charts, we can see that the storage capacity and also the data transfer rate are growing each year. But if we compare the rate of growth by seeing this sequential read speed per gigabyte, we can see that this ratio actually drops. So it shows that data transfer rate grows much slower than capacity. And maybe the data transfer rate is the potential bottleneck. So it makes an important implication on how to process the large data. We want to reduce the data transfer as much as possible. And the traditional CPU-centric method may not work. So we'll need a new method. To design a new method, a new type of hardware called programmable storage may be helpful. So in industry, vendors such as Samsung are trying to design and also prototype these kind of new hardwares. So for a programmable storage, it consists of two major components, storage and compute. Because they are co-located on the same piece of hardware, so compute can access the data inside storage directly, and it can do the computation efficiently. So the new computation idea is, instead of moving data to a computation, we're now moving computation back to data. So previously, the computation is done in the CPU, but now we can offload the computation to the programmable storage, and the compute module can do all the computation. So it can save much data transfer and also save the burden on CPU. There may be some benefits from offloading different kind of operations to programmable storage, but these benefits are really difficult to be realized. The reason is that even though existing frameworks can show a great performance improvement for some operation offloading, they provide no guidance on which operation we should do to offload. And some frameworks may require low-level programming or even different programming paradigms, such as MapReduce. And our project tried to resolve these two issues. So we propose a two-step approach. First, we would like to analyze different operations and understand their characteristics before we finally proposing a systematic approach to choosing which operation to offload. And second, we want to make application development easier. So we want to implement a generic framework for offloading different operations. In detail, we'll be doing our experiments against RocksDB on Vimeo. So RocksDB is a log structured merge tree based key value store, and it is developed within Facebook. Vimeo is a virtual NVMe SSD emulator based on the Cumulus emulation software. So there will be three steps. First, we plan to analyze the compaction operation and try to figure out which part we want to offload. And then we'll implement the compaction offloading to the programmable storage. Finally, after we have finished compaction offloading, we'll try to explore other appropriate operations to offload. With a successful operation offloading, we hope that we can find a proper trade-off between the weak storage processors and also the data transfer cost in order to achieve a better overall performance. And second, we hope that operation offloading can improve resource efficiency and also overall performance. We will evaluate these two hypotheses against the compaction beside RocksDB. We'll deliver one major feature, which is compaction offloading in RocksDB. So we plan to do this within 4 steps. First, we'll separate the compaction logic into a separate process. And this process should be able to communicate with the host via inter-process communication. And second, we'll integrate the separated logic into the Vimeo SSD emulator. So after this step, the computation is now done in the storage device. Third, we'll perform experiments on the new application and compare the performance with the baseline. So for the baseline, we refer to the original RocksDB implementation, where the compaction is done within the application. And finally, after we finish all of these, we want to research further on operations that can be offloaded based on the analysis from compaction offloading. Our project targets application developers who want to accelerate their applications with programmable storage. And there are so many applications that can be beneficial from programmable storage, including data filtering, scanning tasks in database, file decompression, and also intelligent query systems. For our project, we require both hardware and software resources. For hardware, we'll be using the Narwhal node from PDL Lab with Intel Xeon CPU and running the Ubuntu operating system. For software, we'll be using RocksDB and VMU, and also dbbench, which is a benchmarking tool for RocksDB. Now I'll hand over to Sumit for the design process.
Thank you, Juju, for that great introduction. So now we'll move on to the design considerations of the project. Firstly, the basic design principle that we intend to follow is in a system with multiple applications. So we believe that by providing each component or each process its own space to run and reduce the competition for common resources, each process can run and achieve with utmost optimality. So using this principle, we plan to separate and offload compaction process to the FIMU emulator such that the bottlenecks for the transfer of data between host and storage is reduced, and compaction operation can happen with least competition for resource and least dependencies. So the main design consideration here is we are trying to reduce the data transfer cost between the host and the storage, so that we can run compaction in an optimal manner. So first things first, we want to look at RocksDB itself and how it's designed. Right. So RocksDB, as we know, is a key value based database engine, and in RocksDB, key value pairs are sorted and stored together in a file called sorted string table, and multiple of these SST files are grouped together in a level, right? And the database can have multiple levels with the increasing order of size, and each level is has n times more keys than the previous level. And this is by design because we want to have a good balance between read and write efficiency. Next, so what happens is throughout the lifetime of the database, with the manipulation happening on the keys, new SST files are created, and at times it can happen that there are overlapping key ranges in the SST files. And hence, in order to maintain the optimal structure of the database, RocksDB does something called as compaction. So compaction is usually triggered when a given level has reached its capacity size, or it has reached its capacity number of SST files. So at this point, what happens is the database takes all the SST files in a given level, and it merges all the overlapping key ranges, sorts them back, and writes the new SST files back into the storage. And this process it happens in background, and so this is the operation that we are targeting to offload. So this operation is crucial in order to maintain the optimal structure, to have a good trade-off between reads and updates, and also to reduce the database size and prevent it from overflowing. So let's look at the key reasons why we chose compaction as an operation to offload. The first reason is compaction involves reorganizing the entire file structure. So this involves reading all the SST files in a given level, compacting them and writing them back. So it's a very storage intensive operation, and the compaction process itself is also compute intensive. So this gives us a good balance of both CPU and disk intensive tasks where we can realize the benefits of offloading. And the second reason is compaction operation itself is carried out in an asynchronous fashion. So that means at any point, the database engine triggers compaction, and the compaction happens in the background while the actual application is running, right? So we believe that if compaction is pushed down to storage, then the entire compute capacity of the host can be used for the normal operation of the application, and hence making it faster and more performant. So this shows us an example compaction operation. We can see that the 5 overlapping SST files in level I is compacted together to create 4 new files, and it's pushed down to level I plus 1 after compaction. So this is the high-level system architecture of our design. So the 3 components we have are the RocksDB application, the library for in-storage compute, and the FIMU SST emulator, which is acting as a simulator for the SST. So what happens is whenever RocksDB wants to do compaction, so we plan to intercept this compaction call and through libisc, and pass on this call to the FIMU code that is running on the emulator, so that the entire compaction happens on the compute of FIMU SST emulator, and the new SST files are written back to storage without ever having to be transferred to the host side. And once this is done, the compaction response and the updated metadata is transferred back to the application side so that it can update and start serving from the new SST files. So this is a further deep dive into the previous diagram. So we want to highlight that there are 2 major flows in the RocksDB application now. So the left side flow shows us the normal life cycle of the application, where all the CRUD and other operation calls are handled, and they go through the operating system and they access storage in the normal way. But the compaction call follows the right side path, where it is intercepted by the libisc, and we trigger compaction operation through the NVMe interface on Smart SST, and we do compaction using the compute in the Smart SST. So the newly introduced flows are shown in the green blocks. So in order to evaluate our entire system, so we're using this tool called dbbench. So dbbench is a benchmarking tool which is provided by RocksDB, and it already has preset frameworks for us to fill, read, write into the database, and it also has frameworks which we can use to trigger compaction on the database. So it makes us easier to test our database schemas. So what we plan to do is use this dbbench tool and create a database which roughly simulates a real world database with multiple reads, writes, and updates, and take a snapshot of this database and use this snapshot for our experimentation, so that we can produce repeatable results, because we start from the same point. And we also plan to use the compaction statistics API, which provides us information on how many levels are compacted, how many bytes are compacted, and how much data was present before and after, and so on and so forth. So this is a rough milestone plan. So our plan for the spring semester was that understand compaction process itself, and understand the various stages and what metadata dependency it has, and how does it affect the disk and CPU when it's running. So with all this information, we want to take out compaction as a separate module and run it as a separate process initially. So we have reached the profiling stage, and we are working on removing the compaction as a separate process. And going forward, in the fall semester, our major focus will be on taking this compaction process and integrating it with the FIMU, and run it in storage and analyze the performance, and tweak the offloaded operations and remove bottlenecks to gain the most optimal performance. Now I'll hand it to Juju for compaction overflow.
So for results, we'll first mention how compaction works in RocksDB. So compaction can be triggered either manually or automatically. So if a compaction is triggered by automatic compaction, then the job will be pushed to this compaction queue. If the compaction is triggered manually, then this job will be executed directly. So whenever there is an outstanding compaction task and its schedule, then this compaction task will be submitted to the RocksDB thread pools here. Because compaction is a low priority job, so it will only be scheduled in the low priority thread pools. When the job is scheduled, a thread will be assigned to this job, and we'll first check whether this job is manual compaction or not. If it's not manual compaction, then it needs to fetch all the data from the compaction queue. Next, it will check whether this is a trivial compaction. A trivial compaction refers to those who just need to delete some input files or just move some files from this level to the next level. If it is a trivial task, then we just do the job and then return. If it's not, then we'll need to create a compaction job object and start the compaction process. So for compaction process, there are in total 3 phases: prepare, run, and install. So for prepare, first we'll need to separate this compaction job into several small sub-compactions. And then in the run phase, we'll create a thread pool for all these sub-compactions and then run all these sub-compactions until then finish. And in the install phase, we'll write back all the changes back to the database. So just now, we mentioned that we need a repeatable experiment design in order to compare our system with other systems and also to better understand what is going on with this compaction process. So first, we need to get a data set. We choose the key size to be 30 bytes and value size to be 100 bytes because we have checked this workload called UP2X from Facebook. And this UP2X is receiving mostly merge and put workloads, so it suits our needs. And for simplicity, we just use a median value for both key size and value size. For construction, we'll first construct a data set with 50 million key value pairs. And then we'll update some of the key value pairs with the compaction disabled so that all the new data will be grouped in L0 and they will be compacted later from the top level to the bottom. And after these 2 operations, we get a data set with 3.4 gigabytes. And for experiment procedures, we'll need to first restore the data set snapshot, and we'll invoke the manual compaction from the top level to the bottom. And now I'll switch to Sumit for compaction profiling.
So using the data set that was created in the previous step, so we do a comprehensive profiling on the compaction operation. So our motivation here is to understand, when during compaction, where is the time spent? Is it doing IO or is it doing compute tasks, and which stages are taking how much amount of time, right? And ideally, we wanted to find a part or a component in compaction which is the most storage intensive, and it also is doing some sort of compute, so that we can identify that particular phase to offload it to the storage. So first of all, this is the compaction output for the given database. As we can see here, we have 5 levels of data, and the first level starts off with 100 MB, and subsequent levels have 4 times as much data. As explained, the data is distributed with each level has n times data as previous, and this shows us that. So using this data set, we first wanted to check the relationship between the number of keys and the time it takes for the compaction to happen. So as we can see, as we increase the number of keys and subsequently the data size of the database, the time taken also almost linearly increases. So this confirmed our hypothesis on the relationship between time and the dataset size. And using this information, we ran compaction on one particular level, and this is the statistics. As we can see, most of the time for one compaction run is spent on doing the actual compute task for compaction, and that takes up 53% of the time. And out of the IO time, 41% is spent on reading the files. And this is true because before each compaction can happen, it has to read all the SST files in a given level before even it can get started, because it needs to identify which are the overlapping files and how many overlapping keys are there, right? And that explains why read time is much higher than write time, although the amount of data being read and written is comparable. So, and also it's true that write happens in a buffered manner throughout compaction, and hence it's not acting as a bottleneck, right? So, and the other IO operations like syncing and preparing takes up the rest of the portion, but we can see that the majority is composed of actual compaction CPU and read and write. So we can see the same trend for all the levels with increasing amount of time, right? For level 0, 2, 3, 4, the ratio looks almost similar, except that it's scaled according to the data size here. And another interesting thing we noticed is during the compaction run, we also did analysis on the disk and CPU usage. So the graphs here show one compaction run, and initially at the start of time, what happens is the entire data, all the SST files in the given level are being read, and hence in the second graph we can see a very high read rate. And when data is being read, the CPU utilization is at around 50 to 60% on average, but the disk is utilized for 100%. And as the compaction process itself starts, the read rate falls because we have all the data we need. So, but the CPU utilization goes to 100% because we are doing compute intensive tasks. We are updating the metadata of compaction, and at the same time, we are also writing the new SST files back. So, and the next compaction operation starts, and we can see a similar pattern, right? So this was also very crucial for us to know in order to identify the nature of the compaction itself, right? So the analysis from the profiling we did was that the as expected compaction process involves both disk heavy and compute heavy stages, and it has a well balanced mixture of both. And we believe that offloading compaction run phase can actually free up the compute and the disk transfer time for the host side, so that it can yield the host's compute for the normal workflow and make it more performant. So finally, we want to talk about the offloading plan, and I'll hand it over to Jojo.
So as we have previously mentioned, most of the I/O and also computation will be done in this run phase. So that we'll plan to offload this run phase. What we plan to do is we'll wrap all the information for this compaction job into a structure, and then we want to encode it into a string. And then inside this compaction service on the host, we want to send a string to the remote worker. The remote worker is living inside the programmable storage. So it can open the database and then do the computation inside storage, and then get all the data back to the host. And after the host have received all the results, and then it can start execution from this point after decoding all the outputs. So this is our plan for the offloading, and we plan to do this next semester. And here are all the references, terminologies, and our reflection. And this concludes our presentation today. Thank you.
Thank you.
Nice job, guys. I do have a couple of points here. Just give me a second. So I guess you did a great job with the vision, the hypotheses, and the solution. And I think that, from the design diagram, it's pretty clear that you're going to be kind of creating the subcompaction tasks and sort of executing them in the right order, so that everything sort of unfolds, in a, consistent manner. Some suggestions for next fall. I think it would be better to mention what the data set and the metrics are earlier. That came kind of late in your presentation, because you want to motivate the problem by talking about some real world, data set where this could actually have a big impact. And I'm guessing that Facebook data set is a good example of something that you want to, show an improvement on. And then obviously you're going to have 2 copies of rocks running in order to do a comparative analysis. So you're going to have to run the baseline, compaction on any experimental conditions you're going to try out plus yours, right?
Yeah.
Yeah.
Okay. And then do you have all of the measurement that you need already in place? Because earlier in the presentation, you talked about needing to sort of analyze what's going on in order to understand the trade-off, but you've already got results, about the trade-off. So do you need to write any measurement code, or is all the measurement code you need already there?
Yeah, I think for now, we do have the information we need because we already have the entire benchmarking pipeline written, and we can repeatedly generate the data, right? And it's a matter of changing the hyperparameters, and we can generate any volume of data as well.
Okay.
And for the measurement aspect as well, we have already have taken out the statistics API, and we're logging the required metrics, right? And that's how we have the data for the graph.
Okay.
But yeah, going forward, we plan to add more metrics, as required, but we do have a good baseline of metrics that we need to compare.
Okay. Can we go back to the graph that you claimed was almost linear?
Yeah. Yeah.
Yeah. So, I mean, to me, this is not really that linear, basically, except for that step between 3.2 and 3.3, where the slope fell off a little bit.
Right.
It kind of looks super linear. So that was a little squishy. So I think you want to make sure that you tighten that up for the final presentation, and then actually give a more crisp, statement there about what's going on. I agree that it looks good, but it's my job to, make you guys sound like scientists. So let's pay attention to that going forward. So my last question has to do with the Facebook data set, right? So you want to be able to claim generality for your work. And I think, it's great to have a massive data set that's really relevant, for industry, and do tons of experiments on that, because that will really give you guys a lot of visibility in the field. But is there any loss of generality there? Is this key value space very specialized and different from what other companies do? Is it different from, companies that do, analytics pipelines? Is it different from, companies that, do serving of static stuff, where, the read write, ratio might be very different? So that's another question that I'm going to want you guys to say something about when you do your final presentation. I'm not saying you have to have another data set, because this might be enough. But you should think about sort of the characteristics of this data set and whether it really does have enough diversity, shall we say, in the trade-off between, reads and writes and key spaces, that you feel that this is a good test, right? Because you don't want somebody to come to your final presentation and say, well, what about 85% of the industrial workload, which looks like this? Have you thought about that, right? So you want to make sure that you have a good idea of, whether you're losing any generality, by looking at that particular data set. It's got relevance and it's got massive size. But what do you think about the trade-offs there? Do you think it's a very realistic test case that's very general, or do you think it's specialized in some way?
I think the data set we have now is more leaning towards a generality than targeting some specific workload, because we wanted to model the general work case first, right? So
I guess what you're telling me is that the Facebook case is one that has many different processes that are using the RocksDB and have very different profiles in terms of the ratio between reads and writes. So for that reason, this really serves your purpose.
Yeah.
Cool. Okay, so make sure you write something like that, into the sort of maybe what you can do when you come for the final presentation is talk about the data set earlier and kind of what the objectives are, and then why you picked that data set and why you think it's sufficient. There's no reason not to try other data sets if you kind of feel like it. So if you talk with your team and they think what you're doing is awesome and, should be published in a conference, they may ask you to try some other data sets as well. I think for the capstone, this is plenty as long as you discuss, this issue that we just talked about. But, for a conference paper, it might be nice to have a couple of other, data sets just to kind of prove the point.
Yeah, we'll note that down. Yeah, thank you.
Okay. Hey, that's all I had, guys. You did a great job, and you've already got a lot of cool work done already. So thanks very much. Any questions from Rana or Darshit?
Yes, I have a question. What's the biggest risk you guys face in the next semester for the project?
I think the biggest risk is that, so we believe that like right now offloading compaction, like will let the compaction process itself run independently on storage, right? Without a lot of metadata dependencies, so that we don't have to do a lot of back and forth between the host and the storage side. So if that is not the case, and if each stage of compaction needs some sort of metadata or some dependency from the host side, and that dependency might act as a bottleneck, and it might reduce the performance of on the storage side, right? So we need to make sure that when we offload compaction, we should offload a part of it such that there is not too much dependency, and like the storage itself has all the information it needs so that it can perform compaction independently.
So it's a good idea to include something like that in your presentation.
Yeah.
Or your report.
Yeah.
So that's my question. That's from Rana.
Yeah, I think Intel included all the business risk and all of that in the midterm.
Yeah.
Maybe here it was less.
Yeah, so I think in the interest of time, we
That's okay.
yeah.
That's
Yeah.
okay.
I think it's completely okay. I think you missed out on the hubris content too, but I was missing that part.
Yeah.
But no worries. All good. But great job, guys. I'm pretty happy.
Yeah. So yeah, we plan to include the slides in the appendix, right? In the
Okay.
Yeah.
Sounds good.
Yeah.
Right, great job, guys.
Thank you. Thank you.
Wrap it up. I'm sure if you noticed how midterm presentation and all the deliverables helped you, craft this combined one.
Yeah, definitely. Yeah.
Nice.
Can we access Zoom?
Yeah, you can leave the meeting.
Yeah. Thank you, Professor.
Thank you. Bye-bye.